So in last class, we have seen this basic diagram of discriminant function classifier. So the classifier is based on certain function in which the functions are responsible to classify given input x into different categories like omega 1, omega 2, up to say omega c. Okay. So there is a function g1x which is responsible for omega 1. There is a function g2x which is responsible for omega 2, and so on. There is a function gcx which is responsible for omega c. So this basic diagram is for classifying given input x into different groups or categories. So let's see the structure. I'm repeating the things. This is my input x, and it consists of all these different, you can say, features. So x1 is a d-dimensional, x is a d-dimensional vector. I can write like this: x1, x2, up to xd. Now see, if I choose this node is receiving signal from all the input nodes. That means everything being fed here is received by G1x. Similarly, everything fed here, that is x, is received by G2x. Again, you will see that everybody is receiving same input. So input received by each node is same. And then we have to have this G's such that, let us say, they will produce output if the input belongs to them. Okay, so we are going to check. See, what is value of G1x, what is value of G2x, what is value of G3x, and so on up to GCX. Once they are computed for given input x, we will calculate all this, and then we will see which one is producing maximum. Who is producing maximum output? Let us say this G3x is producing maximum, then my classification decision is class 3. Okay, so in this way this will work. Now let us see how we can obtain this G1, G2 and so on. Now here we can use the Bayes decision procedure that we have already seen to find out these G functions shown in earlier diagram. So using risk or using the simple Bayes, we can do whatever we want to do, but we have these two ways. So we can use risk as my function. So I can use the risk calculation equation as my discriminant function. There I just write here minus because I am searching for max, and the risk we calculate is R, say for decision alpha 1 given x, and suppose R for alpha 2 given x. Then we choose minimum between these two, right? To take a decision, we want minimum risk. And say I am choosing for maximum here in my G1, G2, G3, then I just multiply by minus 1. So you can see here a negative here, which makes the things negative, then I can choose max instead of min. So that is what this negative sign is indicating. Okay, now we can proceed further.
Sir, there is a lot of background noise.
Pardon? Can you repeat your question? I could not listen.
Sir, there is a lot of background noise.
Once again, please.
Sir, there is a lot of background noise.
Which diagram?
Background noise.
Your voice is not clear.
Sir, there is a lot of background noise. There is some constant humming going on.
Okay. Now is it fine?
Yes, sir.
Okay, let us say we have the basic equation of the base equation which we have seen already, and we are trying to say use that as our discriminant function. Say this is, let us say this one is gx. Now we are calling this posterior as, suppose, uh, I will write here, rewrite it this side. Say probability of omega 1 given x is equal to probability of x given omega 1 into probability of omega 1 divided by, say, probability of x. So this is the posterior for class 1, and similarly I can write probability of omega 2 given x as probability of x given omega 2 into probability of omega 2 divided by probability of x. So these are two equations. Now suppose I call them as g1x and g2x. Okay, so I can call them as g1x and g2x, and I use directly this equation one. Say let us have the numbers here, say 1 and 2 as my discriminant functions. Okay, say I can draw a diagram here. See, this is my input x. This is going to a function g1x, and then it is going to a max selector, and which produces some output. Then I have g2x, and this is going to a max selector. So thing is, we are now assuming this g1x and g2x to be the base equation that we have seen already. Okay, so I think this should be multiplied. Now see, what happens is, if I choose like this, you can easily find out that there is no use of this denominator p of x. If I throw this p of x from both sides, I need not calculate this actually, then there is no hampering on my decision regarding the classes. Okay, so this will not be probability. In that case, I can call them as g1x and g2x. So what I mean is, if I throw this denominator, there is no problem in my decision. Still, if g1 was winning, g1 will win. If g2 was winning, then g2 will win. Okay, so there is no problem if I throw this p of x from denominator. Now if I take log of both sides, if I take log of, say, equation 1 and 2, then I can write like this. So this product I can write here, say g1x is log of probability of. So we are doing this intentionally because what we are assuming in the next step is that this likelihood function is normal distribution, so that will be of the exponential form. So log of exponential will make the things very simple, so that's why we intentionally take log for both equations. So I just take log of probability of omega 1. Similarly, I can write g2x is equal to log of probability of x given omega 2 plus log of probability of omega 2. Okay, so that will be simplified version of the base equation. Now remember, I am throwing here this quantity first, and then I am taking log of equation 1 and 2. You can note down these steps. These steps may not be there in book, so you may be finding it difficult to understand later on. So whatever is going on, I hope that you are writing on in a notebook. Okay, so do follow this procedure throughout this class. You can ask me questions if you are not understanding, because I have seen your quiz and performance is not up to the mark as per my expectation. Okay, so you have to be on your toes for this particular course. You read Duda book regularly after finishing this class. Okay, we are just starting the chapter, I think 2 or so. We are not far away. Just go through those initial 2-3 pages of chapter 2. You will be understanding the things in better sense. Okay, so that is must at the beginning. Once you are familiar with the terminology, then you can relax a bit. But initially, you have to struggle for understanding the concept. Okay, so in next class, we will discuss what were the problems in your quiz and why you answered wrong. Many of you have answered wrongly. So that we will see in next class. Now, if I do like this, I find out g1x, I find out g2x, then decision boundary will be at g1x is equal to g2x. So g1x is responsible for omega 1, g2x is responsible for omega 2. So whenever g1x is greater than g2x, what is our decision? Our decision is in favor of omega 1. Whenever g1x is less than g2x, our decision is omega 2. And whenever I say g1x is equal to g2x, then I cannot decide the class of particular input. Then I say that x is on the boundary. Okay, so all such x values, if I collect together, then it will make a decision boundary for two classes. One side of the decision boundary is class 1 and the other side of the decision is class 2. So here g2x is greater than g1x, this side of the line, and this side is g1x is greater than g2x. What will happen on this boundary? On this boundary, g1x is equal to g2x, or I can write this as g1x minus g2x equal to 0. So that will be my boundary equation. I can find out boundary equation by just subtracting g1x and g2x. That will give me the decision boundary. Okay, here you can see a boundary like this between, say, region 2 and region 1. So this is a curve which is coming from our base decision. So we are taking into account the product of likelihood and prior. This is product of likelihood and prior. I repeat, this is likelihood, the distribution of X within class. You can note down this line. If you are not able to understand, you note down what is likelihood distribution. It is the distribution of X within a class. What is posterior? Omega 1 given X. It is the chance that X belongs to omega 1. Okay, this is my prediction. When I write probability omega 2 given X, it is the chance that X belongs to omega 2. And probability omega 1 is prior of my class or previous knowledge about my class, and omega 2 is the previous knowledge about the class omega 2. Okay. Now what we can do is we can even say G1x minus G2x as a discriminant function in case of a two-class problem. If there is a two-class problem with us, I just need to classify x either omega 1 or omega 2, then it is called as dichotomizer. The classifier is called as dichotomizer, or class, in other words, it is classifying into two groups. Dichotomizer means classifying into two groups. So instead of designing G1x and G2x separately, I can design G1x minus G2x as a new function gx. Then I can decide omega 1 if G1, this g of x is greater than 0, otherwise I can say it is omega 2. Okay, so if I put it equal to 0, that will give me the decision boundary. So if I take that as my function, say discriminant function, I can subtract these two posteriors. So this is, earlier we have seen this as G1x, and then I call this as G2x in last slide. Okay, so if I subtract G2x from G1x, that will be a new function g of x. Now if you go back, we have this last equation for G1x. Okay, so I rewrite here, say G1x was log of probability of, what was that, x given omega 1 plus log of probability of omega 1. Then my G2x was log of probability of x given omega 2 plus log of probability of omega 2. Okay, then now I want to do this G1x minus G2x. So I write here log of probability of x given omega 1 plus log of probability of omega 1. Now I am writing minus, and then I will write this thing. So this will be log of probability of x given omega 2 minus log of probability of omega 2. Okay, so this is by substituting value of G1x and G2x from previous slide. So you can rearrange this 4 terms, because this thing is likelihood and this is a likelihood, and remaining 2 terms are priors. So I take this likelihood term, the first one, and this third term, then I write in this form. Okay, since it's negative, I can combine this log and write probability of x given omega 1 divided by probability of x given omega 2, and then I combine this particular term with the last one. Okay, then I can write in this form. Okay, so that will be now my g of x. I can use this as my discriminant function. So x is given to this box, so g of x is calculated here. If g of x is greater than 0, my decision is omega 1. If g of x is less than 0, my decision is omega 2. So why I am saying like that? When it will be positive, when g1x is positive or g of x is positive, g of x is defined like this: g of x is g1x minus g2x. So when will be this positive? When the first term is greater than second term. When this is greater than second term, your answer is positive. When g1x is less than g2x, your answer is negative. So that's why I'm saying when g of x is greater than 0, that means it is positive, you will say your input is belonging to omega 1. If it is negative, then you will say your input belongs to omega 2. Okay, I hope you have understood this. Now we have seen the normal distribution form for likelihood in previous classes. So I am repeating that. So likelihood distribution for a normal case is like this. If I draw for one dimension, I assume this kind of a shape. So there will be a mean of this distribution and there will be a standard deviation. Okay, so this will be the case of one dimension, and I can take this axis, y-axis, as probability of, say, x given omega 1. That means this graph is for class 1. So what I did is I just collected all the samples which belong to omega 1, then I find out their mean value, then I find out their standard deviation, or I can say variance. So if I do that, then it is the graph for omega 1, that is, it is just for class 1. I can repeat the procedure. I will go with all the samples which are belonging to omega 2, and then I find out the mean for omega class 2, and then I find out the standard deviation for omega 2, and then this will be called as likelihood of class 2. Okay, so this will be the standard deviation for class 1 and class 2. So what I do is I write this as normal distribution. So n stands for normal distribution, and I will write this as mu1. This will be n1 and corresponding standard deviation. Okay, then I can write this as n2, then mu2, sigma 2. Okay, so these are the likelihoods, and this n computation is given by this formula, say number 1 here. So this formula is for multivariate Gaussian. Okay, multivariate stands for many variables. Okay, when your input x is one dimension, you have a simplified version formula of this, right? You have very simple formula, that is 1 by twice pi. Now put here d equal to 1, so this will be 1 by 2, 1 by 2 into this variance square root, and then e to the power minus half, that is x minus mean divided by sigma and whole square. Okay, so this kind of equation is there for one dimension. Now when you extend that for 2 dimension or 3 dimension or many dimensions, then the generalized formula is this. Now here your input is capital X, that is you have now a vector. So X stands for x1, x2 up to x. How many dimensions are there? D dimensions. Then mu is now mean vector. You can note down this. X is input vector and mu is called as mean vector. Now mean vector is given by mu1, mu2, mu3 up to mu d. Okay. Now this sigma inverse or this sigma is called as covariance matrix. Sigma is called as covariance matrix, which is the relation amongst the different features in your data. So sigma stands for, or covariance matrix stands for the relation between different features. Now how to compute that, we will take example later on. Just time being, understand what are these terms. So sigma is a covariance matrix. Okay. So this is basically, I think it is 1 by n. N is number of samples into x minus mu into x minus mu transpose. So this is the outer product. This is the outer product between two vectors. So this vector is the deviation of given input x. Okay, so I should modify this. 1 second. So I have to add for all the samples for I equal to 1 to say n, and then divide by n. So I should put here I. Okay, so what we have to do, we have to take the vector one by one. So suppose you have a list x1, x2 up to xn. You first of all you find out mean vector for this. How do you do it? So mean vector is given by x1 plus x2. So I do addition of all the vectors that are given to you for a particular class. So this business is for a given class. Suppose I am collecting all the samples belonging to omega 1, then I am adding all the samples which belong to omega 1, and then I'm adding and then dividing by, say, n. Okay, so this is average of all the samples. So this will be a mean vector. Actually, I should write a bar on it so that you will understand this is a vector. So generally we don't write, but you just consider this is a vector. If you are not able to understand, then you just put their bars so that you will remember yourself that this is a vector, this is not a number. When you talk about this mu, in case of 1D, this is simple number. This is a number. This small x is also a number. So we are talking about here only one feature. Now here there is a list of feature in this downside of your screen. So this way we calculate mean vector. Now what we do, we take this mean vector and find out the difference between given input, say ith feature vector and mean. So what we can do is we take x1, then we subtract mu, then we multiply this with x1 minus mu transpose. So this is the outer product. Okay, so since x1 is d dimension, mu is also d dimensional. So this outer product will be d by d cross d dimension. Okay, so this will be a matrix. Then we are adding to this x2 minus mu into x2 minus mu transpose. So this will be another matrix of d by d. Then I keep on doing this for all the samples belonging to particular class. Okay, once this all matrices are added, then I take the average by dividing it by n, and this is called as covariance matrix. I hope you have understood the procedure. We will take example in next class, but right now you try to understand the procedure. Okay, so when you are provided a list of data samples, in this case you first of all segregate data belonging to each category, that is class, say omega 1 one side, omega 2 another side. You take mean of each category. So you will have mu1 for class 1, that is omega 1, then you will compute mu2 for omega 2 and so on. Okay, so these are all vectors. Once you obtain the vectors, you take the samples belonging to each category separately once again. You take the first sample, you subtract mean from it, you take transpose of that and do the outer product. You will get a matrix, keep that thing aside. Then you take second sample, subtract mean and take transpose of it, do the outer product like this, and then you keep on doing this for all the samples belonging to that class. You add all these matrices and divide by n. That will give you, say for example, covariance for class 1, that I can call as capital sigma 1. Then we can find out capital sigma 2 and so on. Okay, so each class, when I use normal distribution, will be defined by two things. I just need to specify, say for example, for class 1, I just need to specify vector mu1, that mean of that distribution, and covariance matrix sigma 1. Then I can throw my data samples. Once these two things are known to me, I don't require those samples. I need not store them in computer. I just store these two things in my computer, and the knowledge about class 1 is known to me. Then I can go for class 2. I do the same procedure, and then I just remember mu2 and sigma 2. Okay, like that I can go for all the classes in my list and just remember their means and covariance matrices. Okay, so that is how we remember the distribution of data for different classes when they are when their data is with us. We process that data and extract mu1, sigma1, mu2, sigma2, and so on. So this process is called as data modeling because we are fitting a normal distribution curve on this given data. So that is our assumption. What we assume? We assume that the data is normally distributed. We have to assume this thing first. So once you assume that our data is normally distributed, then we can compute the, the properties of that data. So how do you remember that data distribution? You remember that data distribution by computing mean and covariance. Okay, so this is the thing. Now what we do is, once I do this, so we have to substitute this information in our discriminant function. Okay, so discriminant function was gix. Earlier we have defined this. Now in that gix, what I do is now I substitute this normal distribution form and I simplify that. Okay, now if I substitute here, this is my likelihood, which is of the form like this, and this is given by this equation, and I substitute, suppose let us say this equation number 1 in equation 2. So I bring this thing here. Now what will happen? This log you have to take for this particular group. You have to take log of this, and simplified version of that I am writing here. Okay, so this will be log of equation number 1. Is that fine? You can check that this is the log of equation number 1. So this is in general we are writing for GIX. I stands for ith class. Okay, so G1x will be the function for class 1, G2x will be function for class 2. So as I changes I equal to 1 to say C, that means I am talking about C different classes. So if I put I equal to 1, this is the equation for class 1. If I put I equal to 2 in this equation, say 3, then it is discussing about class 3. If I put I equal to C, then it is discussing class C. So like that we can proceed. So this is a generalized equation, and we are going to modify this as per our requirement. Now case 1, in case 1, what I am assuming is that for all the classes covariance matrix is same, and that means the features are statistically independent of each other and each feature has the same variance. So what it means is, actually you will see covariance matrix looks like this. So this is sigma 1 square, this will be sigma 1 2, this will be sigma 1 3, and this will be sigma 1d. This will be sigma 2 1, this will be sigma 2 2 square, this will be sigma 2 3, and this will be sigma 2d, and so on. So this will be sigma d1 up to sigma dd square. Now this is different for each class. So if I suffix here I, then it is I will be ranging from 1 to C. And what this first case is assuming that sigma 1 is equal to sigma 2 is equal to sigma 3 up to sigma C. For all classes, matrix is same, and that too features are statistically independent. That means the off diagonal elements in this matrix are 0. So this side of this diagonal and upper side of the diagonal, the entries are 0, and that too the diagonal entries are same. So variance is same for all features. Okay. There are so many assumptions in case 1, so as to have very simplified version of the g of x equation. So what are the assumptions here? Covariance matrix is same for all classes. Okay. Sigma is same for all classes. Then features are statistically independent. That means off diagonal elements are equal to 0. And each feature has same variance. That means sigma I square is same for all. So these are 3 assumptions that we make in case number 1. So if I do that, this my equation 3 is simplified. It's simplified a lot. Okay, so equation 3 is talking about the discriminant function for different classes, and you see that this I variable is running for these two variables, that is mu and sigma, throughout this equation. Okay, now we have mean different, no doubt. For each class there will be a different mean. We are now talking about this sigma term, which is here and here, and we are saying that sigma I is same for all classes. That is our assumption, and that too we have off diagonal elements 0, and the diagonal elements are having same entries. Okay, they are of same value. The spread for each, so the central values here, these central values, they talk about the spread of feature around their respective mean. Okay, and off diagonal elements discuss about relation between two variables. Say for example x1 and x2, if these are the two variables in my vector, then the relation between them is given by sigma 1 2, the first entry here. Okay, now suppose I have xd and let us say x5, these two variables, then the relation x5, say sigma 5d, will discuss about relation between fifth feature and dth feature. Note that the sigma 5d is equal to sigma d5. So they are symmetric. The entries are symmetric in this matrix. So this matrix is a symmetric matrix. Okay, so we will take one example how to calculate all this in next class so that these things will be clear. Right now we will try to simplify this equation number 3. So equation number 3, I can throw this quantity which is common to all. Okay, so this quantity half log of the mod of sigma, this quantity is same because this sigma is same for everybody, so I can throw this quantity. Okay, similarly the first term, say this one is a constant, there is no relation with I for this term, so I is not there, so this is not there, so I can even throw this term. So I can drop these two terms since they are constant. There is no relation between class and these terms. So I can throw that. And this sigma, as I have assumed, is of this type. That is, there is sigma square here, sigma square here, sigma square up to all the dimensions and off diagonal elements are 0. If this is the case, then this product will be simplified to this thing. Okay, provided all sigmas are same and all the features have same variance. Because of this second line, we can write like this. Where this first term now is nothing but this. This is called a norm square of a vector. Okay, so x transpose x is called as norm of a vector, that is length of a vector square. Remember this. Now when I write here x minus mu I, this is a vector, its transpose, and same vector, they are multiplied, so it is called as norm difference of x and mu, norm square. Okay, so this is a shorthand notation for this particular quantity. Now if you actually substitute here this term in this particular thing and expand it, so it will look like this.
Sir, we have another lecture.
Okay, I will stop here. We will discuss this thing again in next class.